Hello everybody and welcome to today's AIRAH webinar. My name is Marie Karekla and I'm AIRAH's Engagement and Program Coordinator. So today's webinar is brought to you by AIRAH and Ecolibrium, and this webinar will look at the NCC 2019 in particular around the new fan performance requirements that are based around the design of the total fan and ductwork system. Just before we get started, if anyone has any questions, please use the Q&A function that's located just at the bottom of your screen, and we will allow for some time at the end of the formal presentation to go through any questions you may have. So now I would like to introduce to you our presenter for today, Ken Thompson, who will be taking us through the session. So Ken, I might pass things over to you. Thank you.
Okay, thank you, Marie. Welcome to the AIRAH webinar on fan efficiency and ductwork system compliance. The relevant clause in the code is part J 5.4 of section J. And just remember, this only covers the fan efficiency and ductwork pressure loss compliance requirements. For ductwork systems, etc., there are other compliance requirements in J 5.5 and J 5.6, but they're not covered in this webinar. The code allows for two approaches to the determination of compliance within the deemed to satisfy provisions: a components-based approach and a systems-based approach. We'll run through both approaches today and show the different calculations and details using a case study. But first, let's introduce the requirements of the code. Component-based compliance. The component-based compliance method 1 looks at meeting compliance for the ductwork, pressure drops and the fan efficiency separately. Each of the components in the system are required to demonstrate compliance. So your ductwork system demonstrates compliance, or your fans demonstrate compliance. So we have the ductwork in the system has a compliance maximum pressure loss values for each part of the ductwork, for straight duct, and also for allowances for bends, fittings, and components in the system. The fans in the compliance requirements, there are two different efficiency calculations based on whether it's a low static pressure fan or whether it's a high static pressure fan. The fans with low static pressure, the efficiency calculation is based on a small p in the formula there. You can see the log of small p, and small p is for pressure. For high static fans, the large P actually refers to the motor input power of the fan. The difference between low and high static pressure fans is a 200 Pascal nominal value. So fans below 200 Pascal are considered low pressure, and fans above 200 Pascal are considered high pressure fan systems. The ductwork static pressure loss is an average loss within all the straight ductwork. You can have sections of the straight ductwork that exceed the 1 Pascal per metre, and you can have sections that are below the 1 Pascal per metre. So it ends up being an average across the index run of the system. So that's the run with the highest static pressure loss in it. And so that gives you your straight ductwork pressure loss average of 1 Pascal per metre. You also then have to take into account fittings, filters, coils, etc., to determine their static pressure losses. And there are allowances, maximum allowances within the code that you use. So also note though, when using a system-based approach, so this is the component approach, when using the system-based approach, the ductwork pressure loss can be higher than the allowance in the code, and you can use a much higher efficient fan, and the fan can compensate for losses in the ductwork. And vice versa. You can have a low efficiency fan and that can be compensated for by the ductwork pressure loss being very low. So the index run consists of straight duct and flexible duct and is assessed across all straight sections of rigid duct and all sections of flexible duct. Flexible duct is assessed as being straight, so without bends in it or kinks in it. Flexible ductwork in any run, so within the supply run or return air run or outside air run of the ductwork in the system, is allowed to be up to 6 metres in length. You're not allowed to exceed 6 metres in length in any of those runs. Just careful when using the calculator. If you do a index run for a system and you have the supply air duct run and the return air duct run in your calculation to determine your total system static, the calculator will only allow you to put in 6 metres of flex. It'll show up a non-compliance if you try to put in 12 metres, but the code does allow 12 metres of flex, 6 metres in the supply and 6 metres in the return run. So just something to watch for there when using the calculator. Coils and filters each have tables in the code. Coils vary based on the number of rows in the coil, and filters vary in pressure drop allowance based on their MERV rating. As you can see on the slide there, the Australian standard ratings are G ratings, and then you've got the US MERV ratings. The code uses the US MERV ratings, so you need to be able to convert your filter performance data across to a MERV rating. Ask the suppliers for details. Other components in the system, so louvers, VAV boxes, etc. There are clauses within the code, so you need to be aware of these. So go through, look at rooftop cowls, attenuators, fire dampers, balance and control dampers, etc. There are allowances within the code. You need to get familiar with those. Okay, for the fan, to determine the fan efficiency, we've got the two calculations or the two formulas there. But you also need to be aware of the type of installation of the fan. So is it a free inlet, free outlet? So that is typically a fan within an air handler, is a free inlet, free outlet fan. Or you've got a ducted fan. So it has ductwork on one side of the fan or the other side. And that determines whether you've got a type A, B, C or D installation. When using the calculator, you put in whether it's got free or ducted inlet or outlet into the calculator. The ductwork pressure loss calculations for the deemed to satisfy compliance and the detailed information we go through all that, and then we get to these fan performance calculations. So in the case study, we'll be looking at a high static pressure fan. So we need to know these regression coefficients. So we have a minimum fan performance grade. That depends on the type of fan, so whether it's axial, mixed flow, centrifugal, etc. We have the fan regression coefficient A, which is based again on whether it's what type of fan it is, but also on the motor input power to the fan. So you do need to know what size motor you are going to be using on your fan before you can do the compliance calculation on the efficiency. And then we also have the regression coefficient B, which again is determined based on the same criteria. We have a question there that I'll answer later on at the end in regards to the coils. For a system-based approach, so that's the requirements for component-based approach, ductwork and fan efficiency. For the system-based approach, it is a comparison. So we'll use an analogy here, looking at a food analogy. If we've got a component-based approach, we've got the individual items of food. So we have the ductwork and the ductwork components, the part of the system, and then we have the fan, which is the other part of the system. And then a system-based approach, we do a comparison of taking the minimum compliant components and working out what the watts per litre per second, that should say fan power requirement is. Sorry, mistake in the slide there. And we then do that calculation and that comparison based on your proposed system. So you are allowed to do a semi-performance based method, which is method 2, the system-based approach. That'll be clearer in the case study, which we'll go through now. In this particular instance, this case study is based on an existing system that was refurbished, and we had to determine whether the fan would meet compliance or not, based on the refurbishments and the ductwork sizing, etc. So it's a basement area of a building that was used mostly for storage, and so we have to go through and determine the existing ductwork, the existing AHU and new ductwork, and work out the index run, and work out the fan static calculation for the supplier branches determined on the index run. In this particular instance, all of the main branches for this particular system ended up with very, very similar static pressure losses. So the index run was actually chosen as the run with the largest airflow quantity on it. That's just a peculiarity of that system that was used. We then get this information and we can put it into the calculator. To get the calculator, you can download it from the website. So directly from the ABCB resources page, that's the address there, and you download the Excel spreadsheet. We then set up the project details. So the building name, description, fans, case study, project number, CS02, whatever you want to call it, designer, and company, their inputs. That information carries through to your reports page at the end of the calculator. And we then go through and put the system description in for the fan, for the unit, air handler 1, the fan tag, flow rate of the system. So in this particular instance, it's 2,390 litres per second. It's the system. And then you'll go through and do the calculated and allowable straight duct fitting allowances, etc., that have all come through because I've completed the calculations on this case study. So then we can go to the fan system page where we input the data. So we select what type of fan it is. In this instance, it's a centrifugal backward curve fan. And part of the reason this particular unit had a centrifugal backward curve fan, but it also managed to highlight a computational error that is in the current fan system calculator available from the Building Codes Board website. So you go through, and as you can see there, we've got the fan inlet and fan outlet, so free and free, because this one's in an air handling unit. And you have the fouling risk. Fouling risk is associated with, say, turning vanes in ductwork, whether you've got other fouling risks within the ductwork system. It does not affect any of the calculations. It's just something that is within the calculator, and you put the detail in there. So the component-based approach, we'll go through the calculations. If we have a look at, after I've input all of the detail into the calculator, which is, I'll show you another calculation on the next page, but having input all the detail into the calculator as shown before, we come up with a compliance value. So we have a subtotal of 351.8 pascals, which is a calculated static pressure, and then I put in a clean, dirty filter difference. So the compliance calculation using the calculator came up with 351.8, and then I added, to determine what my system performance static pressure loss would be, I put in 145 pascal dirty filter allowance. The allowances in the code are clean filter allowances. So the code will come up with a lower static pressure loss for the calculation of the efficiency value than what you will get when using your own calculation. So that table there gave you a comparison. And as you can see on this slide here, we ended up with a design external static pressure for our system of 460 kPa. And we therefore add the coil allowance of and the air handler internal losses and get a 560 pascal, not kilopascal, pascal pressure loss in the system. So our selection for our fan is based on the 2,390 litres a second and the 560 pascal pressure loss. And that would be the calculation for the actual fan power or the fan performance and the fan selection. From a compliance perspective, for the efficiency, what you will end up with is a slightly lower design external static plus the coil. So when using the calculator, the coil is added in to that compliance calculation. But when we select air handlers from suppliers, the supplier will typically make the air handler and coil allowance calculation, and we supply them with the external static pressure. So just be careful. Using the calculator and the compliance within the code is not quite the same methodology and approach that you would normally use in doing your fan specifications for systems. Works perfectly for exhaust systems, etc., where there is no coil and no internal losses in an air handler, but when doing air handlers, you do need to be careful. Your compliance values will be different to what your selection values are. So for a centrifugal backward curve fan, ran it through some fan selection software and came up with this, this particular fan selection, which gave us a fan motor power in the absorbed section of 2.32 kilowatts. And then you have to make a motor efficiency calculation. So you have to allow for the motor losses, which you can get from MEPS. So in this particular instance, I think it was an 83% efficient motor, which then means the motor input power for this particular fan is 2.8 kilowatts. So that's the number that goes into the calculation. So here's the straight ductwork calculation. As you can see, some of the fittings were not compliant, so they show up in red. Most of the fittings and straight ductwork and everything is all green. So from a component-based approach, most of it showed up to be compliant. When we look at the next slide, you can see that the calculated pressure drop for the straight duct and fittings total ended up at the 351.8 as mentioned before, and under the code the allowable pressure drop is 483.2. So the allowable pressure drop from a code perspective is significantly higher than the calculated for the ductwork system. So that at a component level, the ductwork, and as per the table there, it is green. The calculated pressure drop is below the allowable pressure drop, so it's compliant at a component level. That then goes into the determination of the fan efficiency. So the required fan efficiency for this particular system is 51.4%. And that's with our motor input power of 2.8 kilowatts. Yes. So just doing a little bit of testing and playing around and looking at different fans. If we look at using a forward curved, so the fan that we were using was a backward curved centrifugal. For a forward curved centrifugal, we actually have a required efficiency of only 36.1%. If we change it to an axial, it ends up being the same. And if we look at a mixed flow fan, the required efficiency drops even lower. So it does depend on the type of fan as to what minimum efficiency you need for that particular fan. So the fan efficiency can also be checked via a manual calculation. So I'll go through very quickly through the formula and the manual calculation. So for the given fan at the 2,390 litres per second and the 560 Pascal static, which is the full load operating point of the fan, and it's a centrifugal backward curve fan, and we've got the absorbed power of 2.8 kilowatts. We can then input the data into the equation, which I've done here. The regression coefficients, so the type of fan, the N value for the type of fan for a backward curve centrifugal was 64. So in the second line that's been put in. And then the fan regression coefficients A and B work out to be 4.56 and 10.5 for this particular fan and application, which gives a manual calculation of 49.5%. Now, as we noted when using the calculator gave us 51.4. So there is a slight error occurring in the ABCB calculator, which they are aware of, and there should be a new version of the calculator coming out quite soon, which will have this error corrected. So if we look at a system-based approach, in a system-based approach, we can have at the component level, say the index run of the ductwork and the fan system. We can have a non-compliance, but the fan itself will be compliant. and that's because we've got a higher efficiency fan. And overall at a component level, because component level assessment it requires both the index run and the fan to comply, we show an overall non-compliance. But as you can see in this instance, the efficiency and motor power values can compensate for, or the motor power value can compensate for the index run, and we can end up with it satisfying overall. So you can actually go through, and because we've got a more efficient fan, you can end up with a compliant system. So that, in the system-based approach, looks at the watts per litre per second of the fan power for the minimum compliant fan from a deemed to satisfy perspective using the component-based approach, and then compares it to your proposed system watts per litre per second. So just in regards to the system-based approach, it will go through and look at the fan and shaft power absorb efficiency requirements. So to achieve a fan motor input power per unit of flow rate, lower than the fan motor input power per unit of flow rate achieved when applying the component-based approach. So it looks at the absorbed power and takes into account the motor efficiency losses, and then using these equations, you'll end up with your watts per litre per second allowances. These equations are all out of the DA manuals, so you can go through those calculations. So in conclusion, there's two ways to comply for the fan system efficiency and ductwork compliance. So you can comply via component-based or system-based approach. There are impacts of changing fan types on your minimum efficiency requirements. Understanding the ductwork static pressure inputs. So making sure you go through the calculator and understand when and where you need to input certain requirements. It's quite critical, and they are slightly different to what you would use from a contractor or specification level. Make sure you're confident in the outcomes and verification of your design, because as we've noticed here at the moment, the current ABCD calculator has some slight errors in it. It's only a minor error, but you need to be very confident that your compliance is going to meet, your assessment is going to meet compliance. And then also don't forget about ductwork insulation and ductwork sealing for parts J5.5 and J5.6, I should say 5.6, sorry. That's the conclusion of the slides. I'll now just have a look at the question and answer section and see if I can answer the questions that are popping up. So determine low and high static pressure for fans, so that was 200 Pascal. So there's a 200 Pascal. There was some, so for the coil pressure drop figures, where did they come from? Unit manufacturers. Yes, there was industry engagement. Not exactly sure which companies were engaged with, but there was some industry engagement. They'd have to go back to the Building Codes Board and find out exactly who they were, but yes, there were definitely some industry engagement there. For low pressure fan, it is the system pressure in the calculation. So it's the same as we went through and did the system pressure calculation in accordance with the higher pressure fans. It's the same for the low pressure fans as the system pressure. So it's not just the external static, it's the system pressure. Fan input power. No, it is so it's the fan motor. It is the fan. So the fan input power is the fan motor input power. So it's the absorbed power of the fan with the motor losses. So if you've got an 83% efficient motor and you've got your absorbed power by the fan from the fan manufacturer that they need to drive the fan to a certain speed, then you need to take into account the motor losses. Quite a lot of the manufacturers provide the actual motor input power, so they have already taken into account the selected motor and the losses for that particular motor. Will it be updated to reflect the 6 metre flex rule? Don't know whether the calculator will be updated for that or not. Do know it will be updated for the other error in regards to the fan, but don't know whether they're updating the 6 metre flex rule or not. Why is a fan in an AHU type A free inlet and free outlet? So the way that so it's just the way the code definitions are set. The definition of a free inlet and free outlet fan is one without attached ductwork attached directly to the fan. So typically a AHU will have the fan sitting in a plenum or chamber, and then the ductwork will come off the plenum or chamber. So therefore it's free inlet, free outlet. So the full load operating point is the point at which the fan efficiency is calculated. So you do need to do your selections and find out your full load operating points of your fans when you do your selections, and then use that for the calculation of the efficiency. So if you're doing a JV3, so if you're doing JV3 requires you to do DTS calculations for everything to set up the reference model. So yes, you still have to do all of the efficiency calculations or determine your system minimum efficiencies, because that's the data that goes into your reference model, so that then when you do your proposed model with your actual fan, you have something to compare against. We always have to consider absorbed power at the duty point to meet compliance, not nominal capacity of fans, correct? Can I just type correct? How's that? Does that answer that question? Yes, we do consider the absorbed power at the full load operating point. And well, it's the absorbed power plus motor losses. What is this difference between system static efficiency and system total efficiency? I'll need to take that question offline to answer that one. So we might move to the next one. How is duct leakage factored into the calculations and compliance? It's not. What's the relevance of watts per litre per second for the fan selections? Is it now just about fan efficiency? It seems that fan efficiency requirements. That's a fairly difficult question to answer quickly, but there was a large amount of detailed analysis and energy modelling work and fan efficiency assessment work done before the 2019 code was written. And it was believed that the 2019 code was actually going to be slightly more stringent than the 2016 allowances. However, the 2019 code addresses the issue with 2016 around the fact that some fans in the watts per litre per second tables, or some applications of fans, didn't actually have an available product that could meet compliance. So in some instances, you may find it to be slightly less strict for 2019, but overall it is more stringent and requires a higher efficiency. When calculating the pressure drop in a system, we normally allow for dirty filter pressure drop. Yes, we normally do. When using the calculator has an allowance based on a clean filter. So you will get a significant difference between your specified static pressure loss. So yes, there will be a significant. The calculator is it is based on clean filters. That was just a decision that the Building Codes Board made to simplify the efficiency assessment. So the efficiency values are based on clean filter pressure drop allowances. So you should do the same thing in determining your fan efficiency for compliance. Obviously, your selected fan would then need to, from a duty perspective, need to achieve the dirty filter values. Otherwise, you won't get the airflows in your system and you'll end up with performance issues. So yes, it is something to take into account and note. Yes, basically, the Building Codes Board note turning vanes to be a fouling risk. They do not state anything in regards to stream splitter dampers, VCDs, etc., but they do state that any fouling risk should be noted in the system. It only comes up in the report on the calculator. It doesn't affect the calculations, as I mentioned before. So it does not affect static pressure. So it's kind of a, yes, it's something that you put in the calculator, but doesn't seem to have too much impact on anything. Should a DX coil in a ducted system be taken into account when looking at the coil pressure drop? Yes. In reality, flexible ducts are not load straight due to site constraints, etc. Is there a correction factor? No, there is not. No, there is not. The Building Codes Board, in your proposed system, you will potentially have a much higher flexible duct pressure loss, but the Building Codes Board decided that they would do the assessment based on flexible duct being straight and well installed, and not make any allowances for additional pressure losses. So they considered it a method to, I don't know, drive better installation practice. Ask Fantech about if they're going to warrant their calculations. Otherwise, you'll probably need to justify the calculations yourself as well. Can we go with higher friction rate for kitchen exhaust duct? Well, when you look at the calculator, I didn't go through this, but when you look at the calculator, you'll actually see that kitchen exhaust systems do not have to comply. They come up as not applicable. So I'd say the answer there is yes. Kitchen exhaust systems are not assessed. Is this calculation applicable for split ducted and VRV type systems, even though the overall efficiencies are covered under MEPS? So it depends on the size of the system. That's a fairly difficult question to answer. in one sentence. It's a case-by-case basis is what I'm going to have to say there for VRF systems. It will depend on how you set up your VRF system, how it's designed, etc. So, yes, this depends on design, so case by case. What I mean by that is if you've got a dedicated outdoor air system connected to the VRF system, then you've got fan compliance on the ductwork and the ducted system for the dedicated outside air, etc. So it just depends on how you've designed your total system. What are the requirements of keeping records? Professional engineering requirements. As a professional engineer, you need to keep your calculations. Yeah, if the calculation shows a fail for an efficient backward curve centrifugal, can compliance be achieved for the same ductwork using a less efficient type of fan, such as an axial? That's not really a compliance related question. I don't think it's a lot to do with the type of fan and the input power to the fan, and then the efficiency of the airflow delivery for the fan, and different. The reason I showed the calculator showed that different types of fans have different efficiency allowances is for when you're comparing an axial to an axial and a centrifugal to a centrifugal. You're not really, under the code compliance, you're not really comparing different types of fans to each other and trying to achieve compliance that way. Stated ductwork elbows greater than 90 degrees require long radius bends or turning vanes. Any requirements for less than 90 degrees? No. A DX coil for an air handler is not listed when selecting a coil in the calculator. How do we take that into account? The calculator just lists a coil. And it'd be the pressure drop across the coil based on the number of rows of the coil. So a DX coil will have a number of rows and a pressure drop across the coil. So you just use a coil, as far as I understand how the calculator works. Why does the new calculator use MERV ratings when we use GNF ratings as Australian standard? Because a lot of the research and analysis and modelling work that was done used a lot of American data, and the American data uses MERV ratings. So they put MERV ratings in the code rather than converting it. We got through the questions. There we go.
We did.
Thank you, everybody.
We certainly did. No, thank you for that, Ken. And thank you, everybody, for attending today's webinar. Just to let everybody know, this webinar has been recorded and we'll make it available to everybody up on the AIRAH website. And I'll send everybody an email and let you guys all know when that does become available as well. To register or view for any of AIRAH's other upcoming Streamlines, please visit our website. We do have a full schedule there between now and middle of December. So please, visit the website to register. So thank you again, Ken, and thank you, everybody. And I look forward to seeing you all again soon. Thank you. Bye-bye.
Thank you. Bye.